Welcome to this video that introduces network diagrams and basic critical path analysis. Over the next 9 minutes, I'll explain what network diagrams are and how they are used to model a project. I'll then go on to show you how you can calculate the time it will take to complete the project and see where there is flexibility in the way work activity is performed. Network diagrams are a means of modeling the way work can be sequenced in order to achieve the objectives of a project. We start with a list of activities and then arrange them in a sequence that shows how we expect them to be performed. There are two formats: activity on arrow, shown at the top of the screen, and activity on node, shown below. The latter is more commonly known as precedence. This is the format I'm going to use to explain the basics of critical path analysis today. Precedence diagrams are made up of nodes and dependencies. The nodes represent the activities that need to be performed, and the dependencies show how they are related. There are 4 types of dependency, but in this video we'll only use the simplest, which is known as the finish to start. As its name suggests, this indicates that one activity, the successor, cannot start until a previous activity, the predecessor, is completely finished. Before we look at how to perform the calculations, I'll quickly explain the values we're going to calculate and how they are displayed. We start with an activity node that has space for the name of the activity in the middle and 6 boxes for various values. The calculations need an estimated duration of the activity, which is placed in the top middle of the node. Once we have activity durations and a diagram that shows dependencies between activities, we can calculate 5 values. These begin with the earliest start, which is placed in the box on the top left. In the top right, we'll place the earliest finish. The box on the bottom right will be used for the latest finish, and to the bottom left, we will place the latest start. Finally, in the middle of the bottom row we will calculate the flexibility we have in performing the activity. This is known as float. Don't worry about memorizing these, it'll all become clear as I talk you through the calculations. Now we're ready to work through the first phase of critical path analysis, called the forward pass. We've estimated durations in days for each activity and begin by setting the earliest start of the first activity to 0. Activity A has a duration of 2 days, we add this to the earliest start to give us an earliest finish of 2. At this point it's worth noting that some people prefer to begin by setting the earliest start of the first activity to 1. Ultimately this will make no difference to the reports we produce, but will significantly increase the amount of mental arithmetic needed to complete the calculation. Our purpose here is to understand the analysis process as simply as possible, so we'll start with 0. Since activity A finishes at 2, the earliest that activities B and D can start is also 2. With a start of 2 and a duration of 3, activity B has an earliest finish of 5. Similarly, activity D has an earliest finish of 12. C can start as soon as B is finished, so it starts at 5 and finishes at 5 plus the duration of 3, or 8. In the same way, E starts at 12 and finishes at 16. Activity F is different as it has 2 preceding activities, C and D. C can't finish until 8, and D can't finish until 12. F can't start until both C and D are finished, and therefore, can't start until 12. When an activity has more than one predecessor, we take the highest number to calculate its earliest start. With an earliest start of 12 and a duration of 6, activity F's earliest finish is 18. G is preceded by both E and F. Taking the higher of these 2 finishes gives us an earliest start for G of 18. With a duration of 3, the earliest finish of G, and the project as a whole, is 21. Having completed the forward pass, the next stage is to perform the backward pass. We start by setting the latest finish for activity G to be the same as its earliest finish. Starting with a latest finish for G of 21, we now deduct durations to calculate all the latest starts and finishes. The latest start for G is 21 minus 3, or 18. Given that the latest time G can start is 18, it follows that the latest time activities E and F can finish is also 18. Continuing with the deductions, the latest start for F is 18 minus 6 and the latest start for E is 18 minus 4. Activity D has 2 succeeding activities. E doesn't need to start until 14 at the latest, but F has to start by 12 in order to complete the project by 21. Therefore, D has to finish by 12, which means the latest it can start is 2. Using the same logic, C must finish by 12 at the latest and start by 9. This means that B doesn't have to finish until 9 and start until 6. Once again, activity A has 2 successors. B doesn't have to start until 6, but D has to start by 2. Therefore A has to finish by 2 and start by 0. In a simple network like this, if you don't come back to 0 on the backward pass, you've done something wrong. The third and final step is to calculate the flexibility that we have in performing each activity, while maintaining the earliest possible finish date for the project as a whole. I'll illustrate the calculation for 2 of the activities and then fill in the remainder. Activity C can start as early as 5 and finish as late as 12. This gives us a window of 7 days in which to complete the activity. The estimated duration is 3, so we have 4 days of flexibility in the performance of the activity. The calculation is latest finish, 12, minus the earliest start, 5, minus the duration, 3. The result of the calculation is called the activity's float, and it is entered here. If we perform the same calculation on D, we get latest finish, 12, minus earliest start, 2, minus duration, 10. The result is 0, which means we have no flexibility in the performance of this activity. In this example, it is a critical activity. Doing this calculation for each activity reveals that the float of activity A is also 0 and for B it's 4. F is 0, E is 2 and G is 0. If we connect the activities that have 0 float, we have identified the critical path for this network. It's important to note that the correct definition of this is the longest path through the network. It's possible that this may have non-zero float, but I'll cover that in a separate video. Finally, the convention for highlighting the critical path is that we draw the activities and links in red. While network diagrams are perfect for constructing a logical model of a project, they're not so good for displaying how the work progresses over time. For this, we need a type of bar chart usually referred to as a Gantt chart. This starts off with the 7 activities listed vertically and the numbers 0 to 21 along the top. I explained earlier that we would use a numbering system that kept the arithmetic as simple as possible. This is where we convert ordinal numbers, such as 1, 2, and 3, to cardinal numbers, such as first, second, and third, in order to indicate dates. Activity A runs from 0 to 2 on the top scale. As we draw the bar, you can see that this means it starts in the morning of the first and finishes in the evening of the second. Similarly, when we draw activity B from 2 to 5, the lower scale shows it running from the morning of the third to the evening of the fifth. This continues for all the activities. As you can see, I've highlighted the critical path in red and also added the float as thin green bars. We can now do away with the top scale and just use the dates. The result is something that clearly shows the progress of the work over time, where the critical path lies and where there is flexibility in the performance of some activities. This video has dealt with the basics of network diagrams and critical path analysis. There are many additional features that can be used to model a project more accurately, and network diagrams are also the basis for many other forms of analysis, such as resource-limited scheduling, critical chain, earned value, and Monte Carlo analysis. All of these tools and techniques are explained in the Praxis Encyclopedia on our website, and we will regularly add new videos to introduce and explain them. Keep in touch with new developments by following us on LinkedIn, YouTube, or checking the news feed on the Praxis Framework website. Thank you.